for a week, but 2 weeks ago, basically, we had started to talk about and essentially lay the mathematical and notational foundation for continuum mechanics course. And the thing that we talked about in great depth was the two things basically. One was this official explanation or description of what tensors are. सबसे पहला काम हमने ये किया था. And then how we can represent tensors either in the direct notation or in the indirect notation, right? So I hope you all have the recording available as well, and I hope you've gone through the slides yourselves, so I don't need to repeat exactly what had happened. But just very briefly, I just want to reiterate a few things. One was we saw how tensors basically is this very grand universal term for all properties which are independent of coordinate systems. And we discussed how this basically includes all of the physical properties that we've been discussing almost all of our lives. So velocity, mass, even density, and so even color actually, and so on and so forth. These are all tensors which are independent of the coordinate system. So it doesn't matter if I consider the mass or consider my own mass in an XYZ coordinate system or a polar coordinate system and so on. The mass is still going to be, even if I look at some vector quantity such as the force itself will stay the same, only the components would be changing. That is, we do often, whenever we need to perform some operations on physical properties, then we need to project them onto coordinate systems, right? So when, for example, I'm looking at the resultant forces acting on a body, sorry, then perhaps I will need to project them onto a coordinate system so that I can perform addition component-wise, right? But overall, वो resultant force या वो जो individual forces होंगी, वो वैसी की वैसी रहेंगी. बेशक मैं उन्हें XYZ में देख रही हूँ या polar में देख रही हूँ, and so on and so forth, right? So we saw how scalars, vectors, tensors, scalars, vectors, and then second order tensors such as stress and strain. These are all they're all just tensors with different rank. फिर हमने discuss किया था कि ये rank exactly क्या होता है? It's the spatial dependence that a physical property has. Okay, so just the little recap ये सब कुछ था. Now, then we moved on to discussing in great depth what index notation is. So index notation is basically, and I'm so sorry for कितना इसमें घिच पिच हुआ है, लेकिन I'm using the annotated slides that we had from last time. I hope maybe it'll just jog some of your memory. So the point was that we use this subscript I or J or K and so on to represent each of the components of a tensor. So for example, here this UI is representing a vector where ये जो I होगा, क्योंकि हम 3D में हैं, तो I जो है वो उसका each component को represent कर रहा है. That is, I goes from 1, 2, and 3. So U1 उसका पहला direction का component है, U2 second direction का, and the U3 is the third direction का component. Or all of it can just be compactly represented using the index notation like so, UI. So we discussed all of these things in great depth. Uske baad we started to move to look at some of the conventions used in index notation. One main convention was the summation convention, which was if you had a repeated index, इस तरह का, जैसे ये I है, नजर आ रहा है सबको? I एक इंडेक्स रिपीट हो रहा है, then these are known, एक इंडेक्स रिपीट हो रहा है सिर्फ 2 दफा, and these are known as dummy indices. And what this implies is कि इस इंडेक्स के ऊपर लूप होके एडिशन हो रही है. This is quite important. So that's what the summation index is. और अगर कोई भी इंडेक्स हो जो which only appears once, then that's the free index, and so on. और फिर ढेर सारे हमने general rules भी देखे थे. We looked at some tensor operations, which means we looked at tensor addition, subtraction. Subtraction is addition. So tensor addition देखा था, then we looked at tensor multiplication. इसमें we saw how कहाँ गया tensor multiplication. Yes, that there are two types of products, the inner or the outer product. Inner product में you're gonna get at least one dummy index. So for example, here I is a dummy index here. So मतलब ये कि inner product में you get either the same, the same, yes, either the same rank of the product या फिर rank which decreases product का. Whereas फिर we have the outer product जिसमें the rank increases of the product. Right, so just some of these things that we discussed. Then we had moved on to looking at tensor algebra. Yep, इसमें वो commutative or associative laws को देखा था and so on. So I'm just reminding myself a little bit. And then I'd asked you to do some practice. So there were this problem that was in the slides which I asked you to do at home. I hope that many of you have done it. I'm going to keep checking here again and again to come back to see if you guys have any comments in the chat. I also received the notifications on my phone, so isliye, please keep sending any comments that you might have. And again, I will not do this myself. Iski solution bhi idhar hi slides mein bhi maine di thi taki you can check your answers. You are, of course, master students, so self-learning or sort of self-motivation is quite key in all of this. But just in case के कोई लोगों को सिर्फ marks के ही गर्ज से motivation है, I'll also give out an assignment today related to index notations. Okay, जी. So I'll tell you about the assignment details in just a little bit later on. Okay, so as part of the index notation, I had also introduced these two sort of symbols which are used in index notation. One is this Kronecker delta, which is Kronecker delta, delta ij. और इसकी ये खास property ये थी that it's equal to 1 when I is equals to j and 0 otherwise. Okay. So essentially, we saw that if I write that out, that means that I'm writing out the components of the identity matrix. ठीक है, so identity matrix को जब index notation में represent करना हो, तो that is the Kronecker delta basically. उसके बाद Kronecker delta की कुछ identities थी, which are shown right here. Close the animation bin, which are shown right here. So I'd also ask you please go through these yourself to check that they are indeed true. If you want me to do any of this, you have to ask. So otherwise, I've asked you to do it basically. So if somebody's tried, Rabia, I'm just coming. Thank you so much. So Rabia has asked a question, so I will deal with this. अगर जो ये मैंने आपको कहा था Kronecker delta और permutation symbol दोनों की इन क्या नाम है identities को try out करने का, then you have to have done it yourself, or अगर if you got stuck somewhere, then you need to ask me. Please note कि जो permutation symbol वाली identities थी, they are actually not very straightforward. और इनको करना थोड़ा सा it's well worth your time to figure these out कि ये कैसे derive की जा रही है. Okay, let's see what Rabia's question is. What is the difference between the last two parts in this problem? Let's see. Oh, this one, Rabia. पीछे ना हमने अगर मैंने चेंज कर दिया होगा तो फिर ये गड़बड़ हुई होगी. Basically, we had looked at the symmetry of a matrix basically, and we saw how if you have any square matrix, या फिर if we have a second order tensor, then we can split it up into its symmetric and skew symmetric parts. So ये जो है ना aij और ये in the parentheses like so, and in the square brackets, these are the symmetric and skew symmetric parts. मुझे देखने दे मैंने कहीं it's possible कि मैंने इसकी it's okay, a slightly notation मैंने change की हुई थी. So I apologize for this, but इधर भी वो curly नहीं क्या कहते हैं इसे, curl like parentheses ही मुझे इसका नाम पता है, और square brackets ही use हुए हैं. So basically वो उस problem the parentheses like so was the symmetric part of that matrix, and the square bracket one was skew symmetric part. So this was the symmetric part and this was the skew symmetric part. Or we had to find those two. I hope that's clear, Rabia. Please let me know in the chat. Okay, so this is how far we'd gotten last time, which is that we had seen that there is this Kronecker delta and the permutation symbol. Or I want to pick up from right here, basically. So, or isme I'll actually also do one little test of using index notation to see कि हमारी identities कैसे हमारी identity की derivations जो है वो up to mark हैं या नहीं. So just a reminder कि permutation. Anyone with a question? Uzair, I'm going to mute you, sorry. Please be careful to keep yourselves muted unless you have a question. Okay, so permutation symbol, I just want to remind you, in the slides I sent you, I did fix this. I did fix the symbol, and I reminded you that it's the lunate epsilon. इसको lunate epsilon कहते हैं. Which was the one, which is the permutation symbol. And basically what it means is कि इसके जो ये I, J, K indices हैं, the order of the indices determine whether it gives us a value of 1 या फिर it gives us a value of -1 or 0. So agar, if we draw out a nice little circle with 1, 2, 3 written in it, and then we go from 1, 2, 3, draw out something like this, then is order ke andar, if the indices appear, then we get a value of +1. Whereas agar iska reverse order mein aaye, then permutation symbol gives us a value of -1. Right, so that's what the permutation symbol was. Now using this, we can see, I said, right, कि अगर इस order में जा रहा हो, so 1, 2, 3, या फिर 2, 3, 1, या फिर 3, 1, 2, then we'll get a value of 1. Whereas if it's going in the opposite direction, then I get a value of -1. और फिर अगर कोई jumbled up order है, this is 1, 1, 2, या 1, 3, 1, and so on, then I'll get a value of 0. ठीक है, ये permutation symbol था. So now let's see कि ये चीजें introduce हुई क्यों हैं और index notation का actually eventually मकसद क्या है. So just a little taster of that is कि you all recall कि we have we can find the determinant of square matrices, right? If I matrix, we all know now that that's actually a second order tensor, right? So let's assume I've got a second order tensor Aij, और इस Aij का मैंने determinant निकालना है. Now please, you may be wondering हमें determinant क्यों चाहिए होगा. इसका जवाब में अब determinant ढेर सारी चीजों में यूज हो सकता है. So for example, अगर ये this second order tensor was actually representing a parallelogram. यार मैं ये बहुत ही मुश्किल अपने आप को घड़े में खोद रही हूँ, उसमें खोदती जा रही हूँ अगर if I'm trying to find examples of the determinant. But just one example, एक parallelogram की अगर sides को हम as a second order tensor represent कर रहे हैं as each of the vectors, then the determinant of those 3 vectors taken together gives us the volume of that entire parallelogram. ठीक है जी, that's just one example. इसके अलावा भी for loads of other things, even for the stress tensor, we'll see later on that the determinant is used here and there for different physical properties. Sometimes it actually has some meaning, which is why we may need to find the determinant. So please ये मुझसे ना पूछेगा कि determinant क्यों निकालना है हमने. Anyway, so if I want to find the determinant of this matrix, then I think we all know what the determinant of a 3x3 matrix is, right? I like this rule. इसका मुझे नाम मुझे भूल गया है, which is कि आप पहले और दूसरे कॉलम को दोबारा उठा पे लिख लेते हैं और फिर एरोज की डायरेक्शन से वो ये टर्म प्लस होगी, ये मल्टीप्लाई होके प्लस आ जाएगा, फिर ये तीनों मल्टीप्लाई होकर प्लस आ जाएगा इनके साथ, और फिर इन वालों के साथ भी मल्टीप्लाई होकर प्लस आ जाएगा। और फिर जो अगली डायरेक्शंस हैं विच इज के ये सॉर्ट ऑफ नेगेटिव डायरेक्शन के डायगोनल्स जो हैं उनमें माइनसेस आएंगे। ऐसा ही है। सो अब नाउ आई हैव this A13 multiplied by A22 A31 with a minus the product of these three and minus the product of these three, and this will give me the determinant of the matrix if I need to. Now little carefully at this, because I'm now going to start to spot some patterns basically. So if you look carefully, ये तीन पॉजिटिव टर्म्स को जरा देखें पहले सिर्फ इनको। तो इसमें क्या है, A11 A22 A33 and then A12 A23 A31 A13 A21 A32. So can I identify that हर इन तीनों के अंदर पहला टर्म जो है वो सेम रह रहा है, इसका A1 ही है इधर, इसका A2 ही रह रहा है और इसका A3 ही रह रहा है। देखें A1 A2 A3, और इस वाले का भी A1 A2 A3। एक तो ये बात हो गई थोड़ी सी, मुझे इसका एक रीजन है मैं ये करने की क्यों कोशिश कर रही हूँ। सो A1 पहला ऐसा, दूसरे का A2 और तीसरे का A3 रह रहा है। इट्स ओनली कि ये जो नेक्स्ट टर्म है इधर वाली अगली, वो इसकी 1 थी इधर, इधर इसकी 2 हो रही है और फिर इसकी 3 हो रही है। मतलब ये कि 1 2 और 3 पे जा रही है फॉर द फर्स्ट वन। और सेकेंडली इफ आई लुक केयरफुली अगले के साथ भी क्या यही हो रहा है, इसकी 2 3 और फिर 1 पे जा रही है। मतलब कि तीनों तीनों जो इंडेक्स का कंपोनेंट्स हैं वो इनकॉर्पोरेट हो रहे हैं, राइट। द ओनली थिंग टू बी केयरफुल अबाउट इज के इसका ऑर्डर एक्सप्लेन आर्टिकुलेट करना थोड़ा सा, लेट मी हर किसी को अदर एक अलग अलग इंडेक्स से रिप्रेजेंट करने दे। इसका मुझे आई लेने दें, इसका मुझे जे लेने दें और इस वाले के लिए के लेने दें कि ये A1 है और साथ I 1 2 3 तक जाएगा, फिर A2 के वाले का जो है J भी 1 2 3 तक जाएगा और फिर A3 K जो है वो भी 1 2 3 तक जाएगा। बट बी केयरफुल, वी कैन सी कि दे आर बीइंग एडेड अप, राइट, ऐड भी हो रहे हैं। मतलब ये है कि इसके साथ ही इफ आई इंट्रोड्यूस द समेशन कन्वेंशन एंड नोटिस कि इन सब में प्लस लग रहा है, तो किसी और चीज का समेशन चाहिए अगर मुझे कि वो 1 के ऊपर भी लूप करके ऐड करे, 2 के ऊपर भी लूप करके ऐड करे और 3 के ऊपर भी लूप करके ऐड करे आ जाएगी। ये मुझे लग रहा है कि मैं नॉट अ वेरी गुड एक्सप्लेनेशन के अंदर जा रही हूँ। दिस इज एक्चुअली नॉट इजी टू एक्सप्लेन। Let me still carry on and I hope that you might be able to spot the pattern better than I'm explaining actually. And then apologies for this. Please notice that they're all pluses. पहले ये 1 2 और फिर 3 में गया, और ये वाला एप्सिलॉन जो था ये 2 3 1 में गया। मतलब कि पहला A जो है उसका ऑर्डर जाता है 1, फिर दूसरा I जो है इट गोज फ्रॉम 1 2 3, फिर जो दूसरा था A2 का J मैंने लिखा है, दैट गोज फ्रॉम J इज इक्वल्स टू 2 3 1, और तीसरे वाले का A3K, उसमें K is going from 3 1 2. Aren't all of these the loop of the permutation symbol going in the positive direction? 1 2 3 2 3 1 or 3 1 2. So this is actually, oh, I'm not happy with this explanation. I apologize. So this is ये पहले वाले को I could write it actually just as this product of A1I, A2J, A3K multiplied by the permutation symbol IJK. और अगर मैं इसको जरा एक्सपैंड करूँ ना, अगर I'd encourage you to please try to expand this out, and you'll see के वो summation symbols जाने हैं हमें. So that is just this one which will come out to you. No. Can someone help me out जिसको ये ज़्यादा clearly समझ आ रहा हो इस वक्त? Apologies. Anyone? Any volunteers? मैं भी सोच रही हूँ. Meanwhile, also think about the next three terms जिनमें negative term है. It's the same thing happening here. It's A का पहला term 1 है, दूसरे का 2 है और तीसरे का 3 है. So it's still the same. A1, A2, A3 और इसका जा रहा है 1, 2, 3 और इसका जा रहा है 3, 1, 2 नहीं 3, 3, 1, 2 and this one has gone from 2, 3, 1. Okay, so again it's in the positive direction. I apologize. I think I need to see the solution because I'm getting stuck somewhere. Unsure. Apologies, class. I am digging a hole and getting stuck in it myself very deeply. It's in the negative direction. Which one, Adnan?
मैम इसमें फर्स्ट ए में आई आएगा, सेकंड में के आएगा और थर्ड में जे आएगा, क्योंकि जे का ऑर्डर 2 3 1 है और के का ऑर्डर 3 1 2 है.
यही नहीं मैंने लिखा इसमें, देखें. I का ऑर्डर 1 2
जो नेगेटिव वाले हैं उनकी बात कर रहा हूँ.
नेगेटिव वाले में क्या हो रहा है? ये 1.
फर्स्ट में आई आएगा, सेकंड में के आएगा और थर्ड में जे आएगा.
ओके, सो यू आर सेइंग कि इसके अंदर फर्स्ट में क्या आएगा?
आई, क्योंकि उसका
फर्स्ट में
ऑर्डर
I
1 2 3 है.
और दूसरे में
के आएगा.
K and then J. Yes. Yes, सही कह रहे हैं. So from what I've written for the J and K, this would turn out to be that. I apologize that मुझे ये आगे से इसका थोड़ा सा मिस कर रहा है कि कैसे हमने पहुंचना है. लेकिन sorry, let for now take a pause on this, and I'll also go back and take a piece of paper and look at it in more detail again. But just for
मैम
जी please.
इसमें जो आपने सर्कल ड्रा किया है, इसमें ये डायरेक्शन नेगेटिव में जा रही है ना, 1 3 2. इफ यू गो टू 1 3 and 2 then it is clockwise direction, and clockwise direction is negative.
This one is positive. So if you go from 1 2 3, it's positive.
Yes, if you go to 1 3 and 2 then it is it has to be negative.
Yes, it has to be
और
negative.
इसमें जो नेगेटिव नीचे टर्म्स हैं A11 A23 and A32, ये तो बेसिकली नेगेटिव डायरेक्शन में ही जा रही है ना मैम.
कैसे जी? इसका तो 1 2 3 जा
इसका
रहा है.
1 1 3 and 2. If you go to 1 then 3 then 2, it is clockwise. So clockwise is negative, isn't it?
ये देखे ना, ये तो 1 है, यहाँ पे 2 है, यहाँ पे 3 है.
मैम विद इन ये तो आप एक ही टर्म की बात नहीं कर रही थी पहले तो मेरे ख्याल में, कि जिस
और
तरह A11 A23 and A32 इसी के अंदर ही मेरे ख्याल में बात रहकर बात कर रहे थे शायद पहले तो आप.
हाँ जी, मैं जरा सोच ही रही हूँ. एक सेकंड, अगर
इसी
एक ही
में आप
इसी को देखें.
एक ही टर्म को देखें ना, जिस तरह A11 A23 and A32 नेगेटिव की
जी
उसमें सेकंड पार्ट जो आप देखें, अगर 1 3 and 2 उनके सेकंड पार्ट में जो आ रहा है 1 1 2 3 and 3 2, तो इनके 1 3 and 2 दैट मेक्स अ नेगेटिव डायरेक्शन.
1 3 and 2. यस ओके, इसमें ये नेगेटिव बन रहा है। यस, एक ही टर्म को देखना है। ओके, थैंक यू अदान, दैट इज रियली रियली हेल्पफुल। सो आई शुड जस्ट बी लुकिंग एट नॉट, सिर्फ इसी को देखूं अगर, तो इसमें वो जा रहा है 1 3 2, और विच इज अ नेगेटिव डायरेक्शन। सॉरी, लेट्स आल्सो राइट दैट डाउन। अगर इस डायरेक्शन में जाएं हम 3 2 और फिर 1 में, then we get a minus, right? 3 2 1. So here we see it's going from, या फिर 1 3 2 पे जाएं, so I get 1 3 2, which is a negative. Here I go from 2 1 3, which is also a negative, and then finally I go from 3 2 1, which is also a negative. बिल्कुल सही कह रहे हैं अदनान, थैंक यू। यस, तो इसके अंदर भी आई जे के, ये हाँ, ये एक पार्ट तो क्लियर हो गया, लेकिन उससे अगले वाले पे अभी भी I'm a little unclear. I'm so sorry. मुझे थोड़ा सा also have to be a little aware of the time, which is why I will move on from this, ताकि मैं इस पे बहुत ज़्यादा वक्त ना ज़ाया करूँ जब मैं अगर कोई चीज़ गलत कर ही रही हूँ तो। So I will come back to this next time once I've figured it out more clearly. But basically, when we do it properly, बजाय ये कि जो हिश पिश मैं मार रही हूँ इस वक्त, उसके बजाय हम करें, then we can write down, and I'm sorry, I'm going to remove what we've just written. In any case, it was probably wrong. So if we sort it out properly, then what we get is the result for the determinant. It can be compactly represented like this. So the determinant, these 6 terms, can be compactly represented like this using the permutation symbol, such that if we just have the epsilon ijk multiplied by a1i, a2j, a3k, noting here that each of the I, j and k are now being repeated. तो वो डमी इंडिसेस हैं तीनों के तीनों, तो तीनों पे लूप ओवर होके ऐड होगा। इसी जब इसको रिवर्स करें तो हमें ये चीज मिल जाएगी। एंड आई एम सॉरी कि अभी मुझे इसकी फॉरवर्ड डायरेक्शन में काम करते हुए मेरे एग्जैक्टली फिगर आउट मुझसे नहीं हो रहा। द की हियर इज, और मैं इसीलिए आपको कहती हूँ परम्यूटेशन वाला आसान नहीं है, उसके जो पिछले स्लाइड पे एग्जांपल्स हैं उनको भी आप लोग जरा गौर से देखिएगा। right, so essentially in index notation, the purpose of introducing symbols such as the permutation symbol and the Kronecker delta is कि वो हमें कुछ complicated matrix expressions को या फिर tensor expressions को compactly express करना allow करते हैं, right? So this entire long-winded expression can be neatly expressed like so. ठीक है जी? So and then we can then further manipulate if we have any other expression. Imagine if the determinant of aij was being multiplied by another tensor. Then of course we can just use our rules for index notation. Okay, ijk is a dummy, either be repeat or, and then we can have the product multiple whatever was being multiplied by it right next to it, and see ke uske indices ke sath if there were any free indices or another repeat indices or what was happening. So just some compact representation using the permutation symbol and the Kronecker delta. For some results like this, they will be provided to you if you ever need to use them. So just be familiar कि ये epsilon ijk क्या चीज है and so on, और dummy indices कैसे आ रहे हैं. And also do practice some of these identities या फिर results का prove करना, because ये जो अभी मेरे साथ हो रहा है ना, ये आपके साथ नहीं होना चाहिए. Okay, we should be confident and comfortable enough in manipulating indices to prove different identities, basically. Okay, apologies. We will come back to this inshallah next time. Okay, so moving on from that, there's also, abhi tak we've been talking about just single tensors, but I think you all are aware that often we have those physical properties being represented at different points in space and also at different times, right? So for example, often we have, let's say, a body, koi ball thi ya some potato shaped thingy, and when we're performing, let's say, a finite element analysis या any other जो भी हम कुछ analysis कर रहे हो, let's say कि हम उसका stress find कर रहे थे, so what we're going to be finding is कि we're going to find we'll most often get some sort of a stress contour, right? कि पूरा color से represent हो रहा होगा कि इधर क्या stress है, इधर क्या stress है, इधर क्या stress है, and so on. That is, these tensor properties are represented as fields. ठीक है जी? So because they are represented at each point in space for a given body. And these fields also vary with time. So if you are looking at a property at one time, then it will be one thing, and then the field will change as time changes. So the idea is that if you have a scalar property, let's say a temperature profile थी आपने पूरे के पूरे एक body पे plot की हुई, then that would be a scalar field. ठीक? So for example, temperature, density, and so on. Whereas if your tensor was a vector, for example, particles की velocity plot कर रहे थे या particles का spin plot कर रहे थे, and so on, then that would be a vector field, right? And finally, अगर stress strain type के हैं तो उनको dyadic fields कहने के बजाय second order and higher के लिए सिर्फ उनको tensor fields का ही नाम दिया जाता है. So first thing, very often we're actually interested in these field variables rather than just a tensor at one point, number one. Number two, often we're actually interested in what's happening to these fields as we move in space, ya phir as we change the time. That is, we're actually interested in the changes in the field. So we're interested in the derivatives of these fields either with respect to space or with respect to time. So now next we're going to move on to looking at the calculus of these tensors. That is, calculus to aapko pata hai na, it gives us the rates of changes, or it gives us the derivatives or changes in the various things. So how do we represent the derivatives in index notation? So one very important function, the representation of derivative is actually this del operator. Is symbol ko, which is the, I think this is the nabla symbol, nabla, a Greek nabla. I think so. Please do check. If someone can Google and confirm, then please do that. That symbol is known as the del operator. Or what the del operator basically is, that it consists of the derivative in space with respect to the x coordinate, with respect to the y coordinate, and with respect to the z coordinate, going in each of the basis vector directions. या फिर if I write it in हमारी familiar direct notation या vector notation के अंदर, then that's how it's represented. It's the partial derivative with respect to x. Del by del x is the first component. Second component is del by del y. And then third one is del by del z. Okay. So that's the del operator, which is giving us the derivatives in space. So this del operator is actually a vector function, as we can see. It has it has one directional dependence. It has one direction. And it has three then components. So this is actually itself a tensor of first order. I hope that's clear, right? It's a vector. Now this vector can actually be applied, or this operator can be applied to different types of fields, be it a scalar field, be it a vector field, or be it a higher order field. So for example, idhar jo hai na, upar it's giving the example of a कि अगर कोई स्केलर फील्ड होती phi, then उसके ऊपर how does the del operator apply? Then for that case, we get basically the derivative. अदनान क्या चीज रिपीट करनी है?
मैम काइंडली यही डेल ऑपरेटर को कर दें, आप रिपीट कर दें.
So just the point to notice कि del operator के अंदर it सॉरी फॉर मैं आई थिंक आप सबको पता है कि SMME वो हुआ है, तो मैं भी अपने घर में उधर उधर से आप लोगों को आज तो पता नहीं ओ कोई शादी की कोई बारात आ रही है. सॉरी. कैन यू हियर मी क्लियरली, और या फिर आपको शोर आ रहा है?
It's fine, ma'am. Clear ही आवाज.
Thank you. So the del operator contains the derivatives in space. So that is, it contains the partial derivatives with respect to each of the spatial components. मतलब ये कि del by del x है, del by del y is its second component, and then the third one is the derivative with respect to the z direction. Okay, so this is a sort of a spatial derivative है इसके अंदर, not a time derivative. और also notice कि वो तीनों के तीनों मतलब it has three components, each direction का derivative. So I'm just trying to point out that this is a vector, okay, itself, her direction का spatial derivative. That's it basically, Adnan. That's what I was pointing out. So we can apply this del operator to each of the types of field. It could be a scalar field, vector field, या higher order tensor field. So अगर हम एक scalar field के ऊपर apply करें, then उसको grad भी कहा जाता है, by the way. Yes. So this thing is then becomes the grad या gradient of phi. And when we apply it, basically phi इसके अंदर multiply हो जाएगा because it's a scalar multiplication, right? A tensor being multiplied by a scalar है. Yeah, vector being multiplied by a scalar. So we just get the derivative of phi with respect to x, with respect to y, and with respect to z. Okay? So this can also be compactly, is actually often represented compactly using this comma notation. तो इंडेक्स नोटेशन के अंदर हम इसको जब रिप्रेजेंट कर रहे हो तो डेरिवेटिव को कॉमे के तौर पर रिप्रेजेंट करता है. आई थिंक मे बी इट्स नॉट दैट क्लियर, सो आई विल राइट इट आउट अ बिट मोर एक्सपैंडेड. So del phi by del x, where phi is my scalar field, for example, maybe temperature, let's say, then this thing can also be represented like so. Phi, comma, the derivative of phi with respect to each direction. Okay. So notice कि वो x, y, z पे जा रहा है ना, each of the direction. That's why I've got index notation. I can represent it just with I. Okay. Similarly, this can also be applied to a vector field. Now, vector itself would index notation may be represented by ai. ऐसा ही है. So अगर मैंने इसका derivative लेना हो, then वो del operator का मुझे या फिर ये जो x y z है उसका इंडेक्स मुझे किसी और चीज से रिप्रेजेंट करना पड़ेगा, because it's not necessary कि I always have the same direction of a being differentiated with respect to the same spatial direction. So that then gives me, sorry, इधर एक लाइन ड्रॉ कर लेते हैं, a I comma j, मतलब I का a का each component being differentiated with respect to each direction, where I goes from 1 to 3 and j also goes from 1 to 3. ठीक, इसको I do want to expand this out ताकि ये थोड़ा ज़्यादा clear होगा. So this is basically giving me ये ai comma j is a vector ai differentiated with respect to each of the directions. That is, in other words, can also be written as, in index notation, del of in matrix notation, del of a. यहाँ पे ये वेक्टर फील्ड है, लेकिन it's much easier or easier understood using the index notation, which will ये जो ai comma j से, I can see that this means it's del of ai with respect to each spatial direction, del ai with respect to xj. Now if I expand this out, first thing that you can see is कि I और j दोनों free index हैं, मतलब ये कि I भी 1 से 3 जाएगा, j भी 1 से 3 जाएगा, such that this thing itself, ये ai comma j जो है, this is a second order tensor. इसमें दो indices हैं, I भी और j भी. तो इसको अगर मैं expand करना शुरू करूं, so this becomes second order tensor. मतलब ये कि it's a second order tensor. तो अब मुझे लग रहा है कि बहुत पुरानी बात गुजर गई तो लोग भूल गए होंगे. सेकेंड ऑर्डर टेंसर क्या होता था, कोई लेट्स से स्ट्रेस होता था सिग्मा आई जे, राइट. सेकेंड ऑर्डर, इसके अंदर 9 कंपोनेंट्स होते थे, राइट. सो ईच ऑफ द 9 कंपोनेंट्स हियर वुड बी del a1, del x1, फिर del a1, del x2, del a1 with respect to del x3. फिर क्या होगा अगली रो में, del a2, del x1, del a2, del x2, del a2, del x3, And finally, similarly for del A3. Right? What does this mean? Each of A का पहला component A1 differentiated with respect to the first component direction. Then A का वही पहला component differentiated with respect to the second component direction. And then finally A1 वही पहला component differentiated with respect to the third component direction. That is why you're getting, that's why I need to have these separate. इसके लिए I represent हो रहा है और इसके लिए J से represent हो रहा है, क्योंकि A के भी 3 components हैं और असल में spatial 3 directions हैं, तो इन दोनों को अलग अलग indices से represent किया जा रहा है. Okay, I hope that's clear. Please be careful and think about that. If you had, let's say, एक second, if you had AI comma I, then what does that mean? Someone help me out. What does del AI comma I mean?
Rank 1.
Rank 1, correct. No, sorry, not rank 1. Apologies. I need to have a Osama, quick question.
Yeah, ma'am. I'm confused right now between the free indices and the dummy indices after what you did in the matrix here.
What's the confusion?
I mean, you told us that both delta AI and del XJ, they are both free indices, but they are repeating here. Am I wrong?
Osama, please be very careful. I have not, there's no addition here. I apologize for आज मेरे साथ एक इशू ये है कि जिस तरह पहले मेरे पास इरेसर होता था ना, मेरा जो राइटिंग पैड है वो चेंज हो गया, मेरे पास इरेसर नहीं है. द ओनली इरेसर आई हैव इज कि आई हैव टू इरेज एवरीथिंग ऑन अ स्लाइड, which I'm going to do right now. Just Osama, just to make this completely clear, please notice when I have a I comma j, then I am saying that I have del ai del xj. Okay. और अब मैं
Okay.
इसको ना जस्ट फॉर माय ओन ईज आई एम गोइंग टू राइट इट आउट इन मैट्रिक्स नोटेशन ताकि मुझे देखने में आसानी हो. ये पूरा मैट्रिक्स है, नो एडिशंस. मैं एक एक टर्म लिखने लगी हूँ. तो पहली टर्म में I1 J1 होगा, तो आई हैव del A1 del X1. बस ये पहली टर्म है. नो रिपीट, नो एडिशन, नो नथिंग. दिस इज जस्ट द वन टर्म.
Okay.
फिर सेकंड टर्म क्या होगी? I1 ही J2 ले लेते हैं. देन आई हैव del A1 del X2. Again, please notice कोई एडिशन कोई समेशन कुछ नहीं हो रहा इसके अंदर. मैं सिर्फ अलग अलग जो उसकी 9 टर्म्स है ना सारी की सारी वो लिख रही थी मैट्रिक्स नोटेशन में, just so that I could see each of the 9 terms that this thing had. This was a tensor, second order tensor बन गया था ये dyad, because as you said कि I और J दोनों free indices हैं. Is that clear?
Thank you. Thank you.
No problem. So these are free indices indeed. ये देखें I और J, they're not being repeated. They're free. So this is a second order tensor. Now I would just wanted to point out, इसी वजह से मैं आप लोगों से पूछना चाह रही थी कि ये जो ये है AI comma J, this represents this thing. Please be very careful and do think about what is this thing, AI comma I.
Ma'am, is it the trace of this matrix?
Ah, you are spot on, completely right. So AI, again, इस case में I is a dummy index, and if you notice dummy index का क्या मतलब है कि it goes from 1 to 3 with an addition on each of the 1 plus फिर 2 वाला और 3 वाला, और अगर आप वो लिखेंगे then this means del A1 del X1 plus del A2 del X2 plus del A3 del x3, which are these diagonal terms of this ai comma j. ठीक? So thank you, exactly right. So this, be careful, okay, this is something completely different, ai comma I, whereas this ai comma j is something different, right? इससे आपके पास एक डमी इंडेक्स फ्री हो, सॉरी डमी इंडेक्स रिपीट हो रहा है, which means कि आपका वो एक ऑर्डर कम होएगा, so वो वेक्टर से वो स्केलर की तरफ चला गया है, पहली बात तो ये। दूसरा कि उसके अंदर जो समेशन हो रहा है वो आप एक्सपैंड करके लिख कर देख सकते हैं कि वो क्या चीज बन रही है। Whereas here we are getting ai comma j, which is a second order tensor, जिसके अंदर a के हर कंपोनेंट की डिफरेंशिएशन है with respect to each direction of x. ठीक है जी, thank you. So just be careful with okay, what do these things mean, right? So इसी तरह the del operator sorry, can also be applied to a dyad. So in the case of a dyad, there are actually two ways that the del operator could be applied. So one could be a single differential. In that case, for example, we have aij comma k, मतलब ये कि aij का differential with respect to just xk, ठीक है जी? या फिर it could actually be a double differential, in which case it's represented like so, ij comma km. और उस केस में इट्स अगेन इट्स डेल ऑफ ए आई जे वैसा का वैसा, और विद रिस्पेक्ट टू जो डिफरेंशियल है वो एक्स के एंड देन एक्स एम हो रहा है। ओके, आई नो अभी दिस डज नॉट हैव एनी फिजिकल मीनिंग बिकॉज वो पर्टिकुलर कॉन्टेक्स्ट और पर्टिकुलर फिजिकल प्रॉब्लम पर डिपेंड करता है, बट वी जस्ट नीड टू बी क्लियर के हाउ आर दोस फिजिकल प्रॉब्लम्स गोइंग टू बी डिफाइंड यूजिंग द इंडेक्स नोटेशन, राइट? Yes. So we've already discussed. So if it is distinct, then the rank is increasing. So for example, इधर हमने वेक्टर को with distinct differentiation जब की थी तो वो टेंसर बन गया था, उससे सेकंड ऑर्डर टेंसर बन गया था ए आई कॉमा जे से। whereas अगर आई कॉमा आई रखते तो फिर वो वही रहता। ऑलराइट, इधर स्लाइड्स में भी था, मैं ऐसे ही पूरा लंबा लिखना लग गई थी। Okay, so I hope all of this is clear, that we use this comma notation in index notation to represent the del operator, yeah, to represent the derivative in space, basically. Okay, so there are a few other topics as well which are related to index notation, like, and we've already spent quite a bit of time. So what my intention is that, और होता ये भी है कि हम भूल जाते हैं. So for example, अभी अगर हम ये सब कुछ डिस्कस कर लें, डिटर्मिनेंट कभी अभी हमने थोड़ा सा करने की कोशिश की, और फिर आगे when it comes to it we will forget कि what was happening here. So we will discuss more index notation as we when we encounter it. So other things that we might deal with later on are cross products, जो अभी तक हमने नहीं किए, vectors के cross products. There's something called the triple scalar product. We haven't dealt with that in index notation. And then there's actually loads more calculus. So right now we just looked at the grad, which is just the multiplication of the del operator with the field. There's actually also the div and the curl, which is when we have the inner product and the outer product with respect to the del operator. And then there are principal values and directions, which in other words are the eigenvalues and eigendirections. इनको भी represent किया जाता है in index notation, and so on. So I will just deal with these things when we get to them. ठीक है? There are a few topics which I just want to mention outright from the beginning कि हम इस course में cover ही नहीं करेंगे, which is looking at the transformation of Cartesian coordinate systems. Now, what I mean by the transformation is कि often, मैं हम बहुत ज़्यादा in depth नहीं करेंगे. Often what happens is कि let's say हमारा initial XYZ coordinate system U था, अभी मैं सिर्फ 2D representation कर रही हूँ, X था, and then we let's say we change it to some other X prime Y prime direction. So these sort of transformations we are not going to be dealing with in this course. Okay, how to deal with this. I leave it up to you to read up on it whenever you do need to do it in your research or your courses. Secondly, we'll also only be focusing on the Cartesian coordinate system. We will not consider the spherical or the cylindrical coordinates. So the intent behind this is that we'll set up the entire sort of physical problems and natural laws and so on in the Cartesian coordinate, ताकि हम लोगों को उनकी basics cover हो जाएंगी, and then whenever we need to move to other coordinate systems, then वो physics हमारी clear होगी और वो just sort of geometric aspects you guys can deal with yourselves, right? Okay, so sorry, this was I think, yep, मैं समझी थी ये आधे घंटे तक हम मगरिब तक कर लेंगे. So this is the end of index notation, and now let's move to the जी अदनान, आप साथ साथ बताते जाएं जब तक मैं दूसरा स्लाइड्स खोल रही हूँ, प्लीज.
मैम मेरे ख्याल में थोड़ा सा कोर्स में चलने में शायद प्रॉब्लम आ रहा है. उसकी वजह यह है कि शायद मैथमेटिकल जो आप करवा रही हैं ठीक है वो, लेकिन उसको प्रैक्टिकल या फिर उसके एस्पेक्ट्स एप्लीकेशंस अगर साथ साथ करवा दें तो आई थिंक वुडंट इट बी बेटर, क्योंकि अभी जो चीज़ें हैं सिर्फ और सिर्फ मिक्सअप होती जाएंगी और उनकी कोई हमें एप्लीकेशन पता नहीं चल रही. तो उस तरह अगर
अदनान,
आप लेकर
थैंक यू
चलें तो बड़ी
थैंक
बेटर.
यू फॉर योर सजेशन. गेस के मेरा क्या जवाब होना है अभी. आज ये पहला लेक्चर ही अभी तक चल रहा था ना, राइट? दिस वाज जस्ट स्टिल इंडेक्स नोटेशन का चल रहा था. सो देयर इज ऑलवेज गोइंग टू बी इन ए मैथमेटिकली sort of loaded course like continuum mechanics, you are still going to need to have just one lecture dedicated to the maths rather than the physics. So that's what we've covered right now. Or from now, abhi, literally from now, I was moving to the physics of it. The issue is that we can't keep jumping back and forth from the maths and the physics, because there's a particular frame of reference, frame of mind which you need when you're just talking about index notation. So this is basically the research has proven that continuum ko padhane ke liye, this is the more effective approach, unfortunately. So hopefully अब से आपको हर चीज का फिजिकल मीनिंग ही समझ आता रहेगा. डोंट वरी.
ओके मैम.
अच्छा जी. All right, so let me share my screen again. Okay, I hope it's visible. So let's jump into it, right? So you remember that I'd already assigned you textbooks, and the purpose is that आप लोग उसको you have to keep referring to them, and for your help I'm going to pop up कि कौन से sections for एक अगर कोई when we're discussing a particular lecture, which sections of the book we're talking about, ठीक है? So that you can go home and use them for further reading. So this is from Lai, the textbook of Lai, and these sections. So kuch darmiyan mein jumps hain and so on. So please be careful about this. And notice we're already on chapter 3 because chapter 2 was entirely index notation and tensors. And यही मैं अदान आपको बताने की कोशिश कर रही हूँ कि आप किसी भी उसमें कर लेंगे ना ट्राई, वो this is just the more effective approach ताकि आगे का समझ आएगा. Right, okay, so let's move to that. Today we're going to be talking about the kinematics of matter, basically continuum matter, or we'll see shortly कि kinematics होती क्या है, right? अगर आप लोगों को कभी भी refer करना हो कि what's going to be coming up next, I have provided you a tentative course schedule in the first lecture, the introductory lecture. तो उसमें you can take a look at it, okay? Right. So generally, the division of matter that we consider in continuum mechanics is that either you've got solids or you've got fluids. And the differentiation that we have for solids and fluids is based on how they behave when they're subjected to loading. So if what we consider generally is that solids are those are that type of matter which deforms when we apply loading to it, whereas fluids are those materials which flow under the application of loading. ठीक है जी. लेकिन इस description के अंदर थोड़ी सी issues आ सकते हैं already, which is कि sometimes actually you get fluids which may be deforming during their flow. So for example, if you've got a compressible fluid, then they will deform during the flow. And then also what can happen is that you can get solids which can flow if their deformations are large. So this is not a straightforward black and white situation, but general sort of room temperature loadings के ऊपर हम इस किस्म की classification कर रहे होते हैं कि solids deform whereas fluids flow. Oh yes, and then there are also these materials in between जिनके अंदर दोनों की characteristics होती हैं, solids and fluids. You might have heard of viscoelastic solids or viscoplastic fluids and so on. So it is not so straightforward. But in all of this, as you can see here already, that there is some sort of a description of how the body is, how the particles in the body are moving, right? So even in the deformation or in the fluid flow, we are actually talking about the motion of the particles. ठीक? So fluid flow में तो clearly there is motion, but even when a solid body is deforming, there will be some geometric changes to the position of the particles. Now this study of the motion of particles is known as kinematics. And the key aspect of kinematics is that we're just concerned with the geometric aspects of the motion. For example, okay, the position was at time 0, this was the position, and now at time t, this is the position. But we're not concerned कि वो जो change था position में वो cause किसने किया था, right? So my point is we're only interested in the geometric aspects of motion with no regard, with complete disregard कि वो what was the cause of it. That is कि वो कौन सी force ने उसे cause किया and so on, हम उसको देखते ही नहीं है kinematics के अंदर. हम only उस change in position या फिर velocity या acceleration, उसका discussion is all incorporated within kinematics. Okay, so first of all, in our setup of all physical problems in continuum mechanics, we are going to just look at kinematics. That is just the geometric aspects. मतलब ये कि position, velocity, acceleration, deformation, deformation gradients, strains, and so on. That's what we're going to deal with. And then we will move to the next topic later on, which will look at okay, what was the cause of the motion. Okay, later. So abhi we're only looking at the motion, the change in motion itself. Okay, so how do we do that for a continuum medium? So let's start with this problem. Now remember that in continuum mechanics we assume that our object or our body is infinitely divisible. ठीक? मतलब ये क्या, you can keep cutting it to smaller and smaller pieces, right? So that basically means that we have an infinite number of particles. ठीक है जी? तो अब अगर मैंने let's say एक body के अंदर उसको particles के तौर पे represent करना था, तो now this fact that I have an infinite number of particles, that's making it very difficult for me to keep track कि मैं इस particle के movement को आगे देखूं, फिर इस particle के movement को आगे देखूं and so on. क्योंकि मेरे पास एक infinite number है even within just one sort of 1 cubic meter or something like that. ठीक? So what sort of a method we come up with is actually using the spatial positions of the particles to represent the particle themselves. Sorry, this will be more clear in just 1 second. So just want to highlight here, I'll highlight this in just a second. Okay, so consider for example that I have a body initially which is something like this. So instead of considering कि ये infinite particles से बनी हुई है and I can name each of them, let's say name मैं उन्हें कर रही होती as A particle, B particle, C particle, and so on, then I would get stuck because मुझे infinite letters चाहिए. So I couldn't really, this is impossible for me to do. So instead what I'm going to do is I'm going to consider कि जब वो initial इस reference position में थी, let's say at T0, तो फिर मेरा A पार्टिकल जो था वो कौन सी पोजीशन पे था, मेरा B पार्टिकल जो था वो कौन सी पोजीशन पे था. That is, I'm going to use the spatial positions that were occupied by the particles to keep a track or to define their motion. Okay? So rather than naming those particles themselves, I'm just going to use their spatial positions to identify them. Right? I hope this part is a little clear. Because वो spatial position को तो मैं even if I have an infinite number of particles, I can still analyze that the spatial positions that were occupied by them. Okay. So please notice here that I'm going to start to introduce some conventions which are going to be pretty important very quickly. So first of all, what I want to point out to you कि जो मेरी initial positions है ना, I'm going to represent them using capital X. Okay, this is my positions occupied at the reference configuration, that is at a time of t naught. Okay, my initial starting point. Okay, now let's consider at, let's say, a certain time afterwards, my same body has either deformed or it has flowed to another sort of region of space, such that now it's at a time t lying somewhere like so. Then again, I can keep sort of defining the positions of each of the infinite particles in space, but this time around I'm going to use I'm going to use a small x. I'll come to this. ठीक है, ये तो capital X for my reference configuration and small x for my deformed configuration. So just to point out here, this at t naught is my reference configuration, or any motion or any deformation is going to be measured relative to my reference configuration, whereas the one at time t is equals to t is going to be my current deformed configuration. Okay, so as I've already said, that I'm going to use capital X to identify my positions in the reference configuration and small x to identify my positions in the current configuration. अब इस चीज पे आना शुरू करें. Sorry, I forgot to set up the problem in entirety, which is to consider that I'm going to be using a Cartesian coordinate system, which means that I'm going to have my E1, E2, E3 basis vectors. Now notice that because I'm talking about a three-dimensional space, then ये जो मैंने vector x represent किया है, capital X, इसके तीन components होंगे, x1, x2, x3. That is, it's a vector, 1, 2, 3 components हैं. It just has one directional dependence. Clearly, ये देखें एक arrow point हो रहा है, it's leading me to that position. So I can represent it using my index notation like so. Clear? So this is in vector notation and this is in index notation. Capital X for my reference configuration. Now, of course, my deformed configuration, I've told you already that I'm going to be referencing to it using my small x. और small x के भी तीन components ही होंगे, x1, x2, x3. It's my position vector of, let's say, the same particle जो पहले capital X पे था और अब कहीं और move कर गया है in the deformed configuration. This too can be represented in index notation like so. No issue. ठीक. Now clearly कुछ हुआ है और मैंने आपको कहा था कि I'm not going to talk about the cause of it right now, but clearly there has been some motion of the body to go from my reference to the current configuration. And if I wanted to, let's say मुझे अगर उसका cause पता होता, या फिर even just because I'm analyzing the motion, then I can define the mapping which takes this point from capital X to small x. दैट इज कि वो यहाँ से यहाँ स्पेस में कैसे पहुंच रहा है. आई कुड डिफाइन इट ज्योमेट्रिकली. नाउ आई एम गोइंग टू रिप्रेजेंट दैट मैपिंग एज phi or phi, ये भी phi है actually, of the initial position, capital X की. इसलिए it's in terms of capital X. Please notice. ठीक है जी. So so I hope अभी तक तो कुछ इतना complicated नहीं. कोई mapping है जो इधर से इस point को इधर लेके जा रही है. Now if I'm looking at another point, maybe somewhere here, then उसके ये वो भी again that would still be represented as X, capital XI. सिर्फ उसके जो अंदर के components होते, जो values होती, they would have been different. ठीक. और वही values अगर मैं इस mapping के अंदर plug in करती, तो मुझे उस particle की जो कि उस position in space में lie कर रहा था, अब उसने कहाँ जाना है वो पता चल जाता, उसका small x पता चल जाता. Okay. So my point is कि वो each particle of the body is being defined by its position in space. Yeah, this hello. Could someone tell me if you can hear me?
Yes, ma'am, I can hear you.
Okay, thank you. So thank you. Someone saying something else, or you're just telling me that you can hear me?
No, ma'am, there's a question.
Please.
Ma'am, what if the body or the mass or anything that we are considering here moves in the same space?
Hassan, what do you mean? It moves in the
Same space. मैम जिस तरह हमने like दो different spaces define किए और फिर हमने कहा कि ये मास या ये point एक space से दूसरे space में जाए, अगर उसकी moment मैम उसी एक space में हो तो क्या consider करें? फिर हम किस तरह define करें?
हसन वो स्पेस चेंज नहीं हो रही, हमने अपना फ्रेम ऑफ रेफरेंस वही रखा हुआ है. डू यू मीन कि वो इधर से इतना दूर मूव करने के बजाय वो एक बॉडी पहले यहाँ थी और अब वो यहाँ हो गई है? इज दैट व्हाट यू ट्राइंग टू से?
Yes, ma'am.
हाँ, so this is still not a problem for us because again still let's say this was my origin, then still एक point जो initially यहाँ था उसका अगर ये कैपिटल X से डिफाइन हो रहा था, तो अब वो पॉइंट कहीं यहाँ चला गया है और उसका ये स्मॉल x से उसका डिफाइन हो जाएगी न्यू पोजीशन. दैट्स नॉट कंसर्न टू अस. प्लीज डू नोटिस दो कि बिकॉज दिस इज कंटिन्यूअम मैकेनिक्स, राइट, जिसमें हमने अज्यूम किया था कि देयर आर नो स्पेसेस इन द in matter, neither can there be two particles at the same position, right? That's physically impossible. So what's going to happen is कि जो भी particle पहले यहाँ पे था उसको कहीं और चले जाना होगा, वो कहीं और move हो गया होगा. And of course that is physically sensible because it's not, अगर कोई चीज पहले ही वहां थी तो you cannot get another particle at that point in space. Two particles can't occupy the same point in space. Does that make sense?
Ma'am, but then we are following the particle, we are not following the space then. थोड़ी सी मुझे मैम इसमें कंफ्यूजिंग, मतलब जब एक दफ़ा एक स्पेस हमने डिफाइन कर लिया कि लेट सपोज मैम ये आप इस डायग्राम को देखें, यहाँ पे ये जो कैपिटल एक्स हमने रिप्रेजेंट किया हुआ है, ये स्पेस हमने डिफाइन, अगर इसी स्पेस में मैम पार्टिकल की मूवमेंट हो रही हो मैम, तो फिर हम क्या करें?
हसन, मैं आपको यही बताने की कोशिश कर रही हूँ कि ये जो कैपिटल एक्स है ना, ये पोजीशन वेक्टर है, ये कोऑर्डिनेट्स नहीं है. मतलब ये कि कोऑर्डिनेट्स दोनों के एक्स वाई जेड ही हैं, रहेंगे. सो द पॉइंट इज कि वही पार्टिकल इवन दो वो अपने ऊपर पहली वाली पोजीशन से उसका थोड़ा सा कोई ओवरलैप भी हो रहा होगा, इस पार्टिकल की पहली पोजीशन को कैपिटल एक्स से रिप्रेजेंट किया जाएगा और उसकी न्यू डिफॉर्म्ड कॉन्फ़िगरेशन को स्मॉल एक्स से रिप्रेजेंट किया जाएगा. even though or even if it is still in the same region of space that it was occupying beforehand. अभी आई थिंक आपको थोड़ा सा और आगे चलने दें, वही हमेशा कंटिन्यूम के साथ, या फिर एटलीस्ट मे बी मेरी बैड अप्रोच के आई आस्क यू टू प्लीज कैरी ऑन अ लिटिल बिट, और अगर वही चीज क्लियर ना हो आगे चलने से भी तो फिर वी विल कम बैक टू इट. ओके हसन? ओके हसन? Hello.
Thank you, ma'am.
Okay, thank you.
Yes, ma'am, it's okay.
Okay, so let me come back to my small and capital X again. So my point was that I've described this mapping which takes it from the original reference configuration to my current configuration. So what I could do is that if I wanted to find out कि मेरा एक new position क्या होनी थी एक particle की, then I could represent my small x as a function of कि वो ही mapping as a function of कि उसकी original position क्या थी, मतलब उसका x1 x2 x3 क्या चीज था, what were the its initial coordinates, और अब क्या time हो रहा है, such that this mapping will then give me its new position. Please notice as I'm trying to explain to Hassan कि ये capital X के अंदर ना values होंगी, ठीक? तो मतलब अगर मैं इस point पे थी initially तो इसके अंदर it will contain those values. So if I plug those values in, then I'll get to my final configuration, noticing that it depends on each of the components. X, Y, Z component of the initial position पर depend करेगा, which is basically कि वो कौन सा particle था और अब क्या time है जिससे हमें पता चलेगा उसकी new position क्या है. Okay, so whenever we describe the new position or even any other physical property in terms of its reference configuration, that is in terms of the capital Xi, then it is referred to as the material या फिर the Lagrangian description of space या फिर of that particular property. Okay, so it's basically जब हम capital like अभी मैं इसकी examples थोड़ी और आपको clarify करती हूँ. Whenever
मैम एक क्वेश्चन था
जी
एक्स आई आपने जो लिखा है हम जो सा कह रहे हैं कि डिफॉर्म पोजीशन जो सी है वो हमेशा जो है ना वो स्केलर का मल्टीपल होगी, तो हमारे पास जो है ना वो डिफॉर्म पोजीशन आ जाएगी जो हमारे पास एक्चुअल पोजीशन है. यही आप बताना चाह रही हैं कि हमेशा डिफॉर्म पोजीशन स्केलर मल्टीपल होगी किसी एक्चुअल पोजीशन का?
एक सेकंड sorry for that confusion. इधर ये phi जो है ना, this is a function, it's just like function of, this is not a scalar, it's a function of x comma t. function नहीं लिखते होते इस तरह f of.
So, ma'am, you are trying to say that this phi is a function of initial position and time.
Yes, so this mapping phi is just a mapping right now. It's okay, ये जो mapping you पहली position से अगली position पे जाएंगे, it's a function of the initial position and whatever time we're at right now. Apologies for not stating this. ये multiply नहीं हो रहा इनसे, ये this is a function of x1 x2 x3 and of time. Okay, let me use an example in just a little bit to explain that in more detail. Let me use, I need a blank slide to go into an example. Apologies. Okay, so let's consider that I have my initial position like so. ठीक है जी, so ये मेरा capital XI हो गया, reference T0 पे थी मेरी positions. So this will be my capital XI. Okay, and then I move on to मैं हसान वाली चीज यूज करने लगी हूँ, which is कि वो उसके ऊपर ये भी overlap भी हो रहा है उसका, फिर भी new position है ये उसकी. So then this time around that same point or same particle actually has moved to small xi at a time pt. नाउ द मैपिंग से मेरा क्या मतलब है कि व्हाट इफ मुझे पहले ही पता हो कि मेरी जो x की 1 पोजीशन है दैट इज एक्चुअली गोइंग टू बी अ फंक्शन, सो पहली उसकी पोजीशंस हो गई ना x1 x2 x3, और फिर उसने आगे जाके कहीं मूव कर जाना है इनटू x1 x2 x3, तो लेट मी अज्यूम कि मुझे उसके ईच कंपोनेंट की कोई एक्सप्रेशन पता है, मतलब ये कि मुझे उसकी ईच कंपोनेंट की एक्चुअली मैपिंग पता है। सो फॉर एग्जांपल x1 के लिए मैपिंग हो रही है जी कि वो इट्स अ फंक्शन ऑफ कि x1 में प्लस कर दें 2 टाइम्स x2 प्लस साइन ऑफ x3, कुछ अजीबो गरीब, मैं अपने से लिटरली मेकिंग दिस अप, बट इट्स पॉसिबल कि दिस इज द मैपिंग कि x1 की पोजीशन आप, और टाइम तो है ही नहीं इसमें, लेट्स से इट वाज tx1, फाइन, doesn't मतलब it's just for the sake of an example. So this means कि you see it's not मतलब okay sure this is a scalar expression, but my point is this is what I mean by a mapping. This is what I mean by a function of x1 x2 x3 and of time. So I'll have this for each of x1 x2 and x3. Right? इससे थोड़ा सा क्लियर हुआ कि मैपिंग से मेरा क्या मतलब है, ठीक, कि मैं आई कैन फाइंड माय पर्टिकुलर एक्स, जो भी कोई कोऑर्डिनेट है, इन इफ आई नो माय इनिशियल पोजीशंस एंड द न्यू टाइम दैट आई एम एट. Okay, so okay, I hope that that clarifies it a little bit, right? But moving on now, this the definition of this thing कि अगर मैं represent कर रही हूँ अपनी new position को small xi को in terms of my reference position capital xi के, then it's known as, उसका नाम है एक खास, तो ताकि you should know this because whenever someone is saying कि Lagrangian description है, then that means कि वो reference configuration की terms में define की जा रही है कोई चीज. I use my reference configuration to sort of describe those particles or to describe their positions at a new time t or their temperature at a new time t and so on, then I'm using the material or Lagrangian description. And why this is important is because this description is most commonly used in solid mechanics. Whereas it's actually also possible for me to do the opposite, which is to always be defining things in terms of the current position, in terms of the small xi's. So for example, I could use the inverse mapping to represent the reference configuration. मतलब ये कि मैं कहूँ अच्छा मुझे इसकी final position पता है कि at अभी जो भी time था उस पे ये small xi पे है, लेकिन अगर मुझे t naught पे निकालनी हो उसकी position, then I can use के okay same यही वाला particle originally t naught पे कहाँ था, उसका capital xi क्या था, लेकिन मकसद ये हुआ कि when I do this I am describing a property in terms of small xi. मतलब ये कि particle की current position की terms में I am describing, let's say, its temperature or its stress or whatever it may be. Then in that case, this is known as the spatial या फिर the Eulerian description of position. Okay. And this one is important जब भी whenever someone says कि I'm using an Eulerian उसका velocity in the Eulerian components है, because this one is used most commonly in fluid mechanics. अभी I'll explain shortly to you कि why is it called the material description or why is it called the spatial description in just 1 second. Please
मैम
note
जो अभी आपने
जी
मैम जो अभी आपने फाई इनवर्स यूज किया है, अब वो फंक्शन होगा स्मॉल एक्स और टी का, ऐसे ही है?
ऐसा ही है बिल्कुल. बिल्कुल ऐसा ही है.
बस यही पूछ रहा था, ये कंफर्म करना.
ठीक है. सो हसान का जो सवाल था उस पर आई जस्ट वांट टू क्लैरिफाई टू यू कि ये जो मैपिंग है फाई एंड इनवर्स फाई, ये सिर्फ एक 1-to-1 मैपिंग ही होगी. मतलब ये कि इट इज जस्ट it's because of our description of a continuum matter, it's not possible. एक सेकंड, इसके लिए अगले स्लाइड पे जाते हैं. It's not possible कि मेरा एक पॉइंट पहले यहाँ था और अब वो आके यहाँ आ गया, और मेरा एक और पॉइंट, let's say, oh, let me, color, मेरा एक और पॉइंट जो यहाँ था, सॉरी ये क्या हुआ, एक और पॉइंट जो यहाँ था वो भी उसी मैपिंग से वो भी उठ के यहीं आ जाए. This is just not possible. Why? Because we are talking about a continuum matter, और एक ही point in space cannot be occupied by two particles at the same time. That does not make any physical sense. Remember, we are not talking about quantum mechanics, जहाँ पे electrons की कोई probability हो जी के blah blah. No, none of that, right? This is nice macroscopic continuum classical mechanics. So you cannot have two particles at the same position at the same time, which is why this phi is actually a 1-to-1 mapping. और क्योंकि वो 1-to-1 है, इसी वजह से उसकी एक inverse भी exist करेगा. And we can always, if we know phi, then we can find the inverse mapping as well. Right. So just wanted to point this out. What time is it right now? 6:41. Okay, I think we can carry on for just a little bit, ताकि ये at least material description को हम अच्छी तरह explain कर लें. So, as we've just seen, if we are describing a property in terms of the reference position, capital X's, then it's known as the material या फिर Lagrange description. And when we're using the small x's, that is the current position, then it's known as the Eulerian description. Now, I know कि अभी तक तो मैं सिर्फ उनकी positions को ही describe कर रही थी using the reference or the current. But what this basically means is कि you could be describing any physical property. So, for example, I have a body जिसका मैं temperature field को describe कर रही हूँ. So, if I describe the temperature field using, again, sorry, मैं जब यूं करके लिखना शुरू करूं T as a bracket open, then I'm trying to write it get temperature as a function of, okay? So temperature as a function of, if I describe it using capital X's and any time T, then this is my material description क्योंकि मैंने reference position use किया. But if I used my same temperature field, but instead use small x to describe it at any time t, then I'm using the spatial description. Okay. So it's just two ways to describe any physical property of a body or of a continuum. Or the reason why we need to be clear about each of these is because, as I said, okay, this one is used in solid mechanics, whereas this one is used in fluid mechanics. Now, what do these mean physically? Now, Lagrange description को हम इसलिए material description कह रहे होते हैं, इसलिए क्योंकि हम basically उसकी original reference position को use करके एक material particle की बात कर रहे होते हैं in time. कि रेफरेंस कॉन्फ़िगरेशन ये थी ना उसकी कि ये जो पार्टिकल है इसका क्या टेम्परेचर होगा at t is equals to 1, at t is equals to 2, at t is equals to 3, and so on. That is, we're following a material particle in time. Whereas, if I use my spatial description, then what I'm doing is that I'm stuck looking at this point in space. और अब मैं अगर at t is equals to 1 उसके थ्रू जो भी पार्टिकल गुजर रहा होगा मैं उसका टेम्परेचर नोट कर लूंगी. फिर at t is equals to 2 उसके थ्रू probably कोई और पार्टिकल गुजर रहा होगा. I'll still just be looking at this point in space and looking at its temperature. That is, we're actually just we fixed our sort of view to a region of space I'm sure you're familiar with this concept. We tend to use control volumes, right, in fluid mechanics. That is, हम एक fixed region of space को देखते रहते हैं और उसके अंदर क्या हो रहा है हम उन properties को note down कर रहे होते हैं. So that's why this description is known as the spatial description, whereas the reference configuration wali is known as the material description. Okay, so material description and spatial description. Be careful about these two. That's what they're meaning. Any questions about material or Lagrange description? या फिर spatial and Eulerian description?
मैम स्पेशल डिस्क्रिप्शन के अंदर हमारे पास टी की जगह पर टी नॉट आएगा जो आपने अभी डिस्क्रिप्शन लिखी हुई है यहाँ प्रेजेंटेशन के बिल्कुल टॉप के ऊपर
स्पेशल में या मटेरियल में?
स्पेशल डिस्क्रिप्शन में.
स्पेशल में. ओके, सो हियर ये जो मैं अभी डिस्क्राइब कर रही थी ना, आई एम लुकिंग एट द टेम्परेचर फील्ड एट डिफरेंट पॉइंट्स इन टाइम. दैट्स व्हाई आई एम सेइंग इन दोनों में टी ही रहेगा, राइट? So because I'm interested in the temperature at T is equals to 1, then I'm interested in the temperature at T is equals to 2 and so on. But वो जो particle या फिर position in space जिसका मैं temperature देख रही होंगी at T is equals to 1 या T is equals to 2, that is either being described using the Lagrange description या फिर using the Eulerian. That's why this will both be just T. Now, I expect that somebody is going to ask me. Actually, I'm just going to wait if somebody is going to ask me. Does that clarify it?
Yes, ma'am.
Okay. What I was expecting, I'm going to ask myself, which is कि इधर तो मैं xi की with t कर रही हूँ और capital xi को with t not कर रही हूँ. Please have a think about this. Okay, why in this position key description, why I have a T here and a T not right here. I've got the azan happening right now, so I'm gonna take just a few minutes break. Meanwhile, you think about this.
Well, ma'am, I think that we are interested in the second part. We are interested in initial position. That is why we are taking T naught here, not T.
Yes, thank you, Adan. Exactly right. So the only reason why the time is not really part of the Lagrange or Eulerian description. Because time is actually कौन से time पे you're interested in the property, right? So for example, when I'm interested in the new position of a particle, then I'm interested in different times, hence why it's T. Whereas when I'm interested in the reference position, then I'm actually interested in T naught, and that's why there's a T naught right there. ठीक? इस वजह से this is how it's popping up. Agar if I, let's say, agar for the temperature field, for both of these, for either of these, I was interested in T naught, मतलब ये कि time is equals to 0 के ऊपर, but I could have just have a T naught right there. लेकिन just the issue with that is कि T naught के ऊपर जो xi है, वो भी capital X ही है, क्योंकि initially तो वो उधर ही present है ना, right? That's why that doesn't really make sense, and that's why I had T is equals to. Okay. So I hope that clarifies. Any other questions? Please keep thinking. Just either I also just for your reference, because inshallah you'll all go on to do big things. I want to point out that Lagrange or Euler जो थे वो when were they operating, so to speak? So Lagrange is there 1736 to 1813, and Euler was alive, born in 1707 and died in 1767. So these two are the ones who are to blame for these two descriptions. But the idea is कि अभी तो हम बड़े इसको systematically पढ़ रहे हैं. Obviously, continuum mechanics is a field that's developed over time. But even this 300 years ago, Lagrange जो था वो he was using the reference position to describe various properties, whereas Euler was using the spatial ones. But of course, what's coming to follow, उन्होंने इतना systematically उस सब कुछ को आगे वो लेके नहीं चले थे. But still, there इन्हीं के नामों पे the descriptions continue. Right. Okay. So let's carry on with one small thing, and then I'll have a little bit of a break. Yes. So which is कि अभी previously हमने going from the reference to the current configuration, I'd used a mapping. लेकिन एक और there's another way to represent this, which will be used frequently later on. That's why it's a good idea to have it to begin with, which is कि हम एक displacement vector भी define कर सकते हैं, which takes a particle from its reference position to its current position, right? So clearly I can see that if I use just vector addition, then I have that small x is equals to what? Capital X plus u, ऐसा ही है, right? So this thing u right here is known as the displacement vector, or the displacement of a particular particle. Now notice that the u is also a field, because the displacement is dependent on where you are looking at on the body. So either इस वाले particle की ये u is a function of this capital X, such that अगर मैं इधर जाऊं, then maybe उसकी displacement जो हो वो कुछ और हो रही हो, छोटी सी कुछ हो रही हो. ठीक? That is, we're not just looking at some sort of rigid body translation या motion, but actually also incorporating within this displacement vector any deformations that may be occurring in the body. Okay, so just to just wanted to point that out. Right, so again, this is a vector. So if I write it down using index notation, I can just use one subscript for it, where I will go from 1 to 3. But also notice कि अभी जिस तरह मैंने draw किया हुआ है ना, arrows की directions and so on, I'm actually describing the displacement as a function of its reference configuration. That is, I'm describing the displacement in the Lagrangian description, or the material description. That is, I've got my u as a function of x. Okay, or as a function of capital X. So just wanted to point that out. Now, एक और इधर थोड़ी सी thing that needs to be described in quite very carefully, which is if I was to write this in index notation,
मैम
हाँ जी,
ये लास्ट इक्वेशन में t की जगह t नॉट नहीं होगा?
not quite, because imagine कि मैं उसकी let's say इस p of t, ये t is equals to 1 पे उसकी position है. इसके बजाय अगर मैं t is equals to 2 वाले पे पहुंचना चाहूँ इधर, then of course इधर से उसका u कुछ और हो गया ना. अब ऐसा ही है. That's why this is just a t. मतलब ये कि it's the displacement at any time. t is equals to 1 पे ये displacement थी, t is equals to 2 पे ये displacement है, t is equals to 3 पे कोई और displacement होगी. Is that clear?
Okay, ma'am.
Okay, thank you. Okay, right. So just one thing that I want to be very careful about. एक second. So there, okay. Thank you. Somebody else has done it. उमर आप क्या कर रहे हैं यहाँ? चले मैं बाद में उमर से बात करूँगी. Okay.
मैं इम्प्रूव कर रहा हूँ.
चले इंशाल्लाह उमर. Right. Yes, so हाँ, I wanted to write this. ये जो मैंने अभी vector notation में या direct notation में लिखा हुआ है, I want to write this in index notation just because I will be using it later on to manipulate some expressions. I want to do it very carefully. इधर तो मैंने I just written down कि वो vectors हैं और उससे ज़्यादा मैं कोई ज़्यादा deep explanation नहीं कर रही थी. Now please focus on this expression right here. ठीक है? इस पे please observe कि the displacement u is a function of capital X. मतलब कि u के अंदर एक वेक्टर है पूरा which is a function of each of x1, x2, x3 and then of course their time. ठीक? और u भी notice it's a vector. मतलब ये कि u के सारे components. This implies अगर मैं इसको as vector notation में लिखूं, then u1 is a function of x1, x2, x3 and the time. फिर u2 is a function of उसी तरह x1, x2, x3 and time. And similarly u3 is also a function of each of them. ऐसा ही ना, ये बात अगर मुझे थोड़ी और expand करनी हो तो मुझे बताइएगा, then I can do that. लेकिन my point is it's not just necessary कि displacement in the x direction is only dependent on the x in position. The displacement in the x direction could actually be dependent on each of the x, y and z components and so on. ठीक है? Which means कि this is actually कि अगर मुझे इसको index notation में लिखना हो, so I have to be very careful to use different notations for this. क्योंकि what's happening is कि u is an I which is going from 1 to 3 but is actually dependent on x के तीनों अलग अलग components. So I can't, if I was to use I right here, then that would have meant कि अगर I1 है, that is u1 find कर रही हूँ, then it's just a function of x1 and time. है ना? और u2 है, then that's just a function of x2 and time. But that's just not correct. अभी आपको कह रही हूँ कि u2 जो है वो तीनों पोजीशन, तीनों कोऑर्डिनेट्स पे डिपेंड कर सकता है. So u2 is a function of x1, x2, x3. So if I want to write this in index notation, I have to be very careful to use a different notation for x, which I'm going to do is that I'm going to represent it with j. Okay? ये I hope कि ये सबको थोड़ा सा क्लियर हुआ. लेकिन इधर please be very careful. Okay, here this thing that I've just written down right now, वही पहले जिस तरह मुझसे किसी ने पूछा था. Here I'm talking about a function. ठीक है जी, I'm saying कि u is this is a function of x, capital X. This bracket is representing a function. It is not talking about a product. Which is why इधर I और J ना free है, ना dummy है, ना कुछ भी नहीं है. ठीक है जी. इधर this is just representing कि I भी एक vector है और X भी एक अलग vector है. That's all that I'm doing with this sort of a representation. Okay, let me repeat this. That these parentheses are representing that this is a function. So by writing it as ui is a function of xj, all I'm saying is that u is a vector, क्योंकि I है उसका, which depends on another vector and time. Okay. And the reason why I haven't used the same subscripts for both of them is because if I'd done that, then that actually implies that one component of u, for example u1, अगर मैं इसको लिखती तो, then that would have become कि u1 is just a function of x1 and time, which is not true. u1 x के तीनों components पे depend करता है. Is that clear?
कि वो एक ही x1 पे भी लाई कर सकता है, जहाँ डिपेंड हो सकता है.
It is okay. अब हाँ possible है बिल्कुल, लेकिन that'll be like a very specific example, right? Generally speaking, u is going to depend on each of the components of the position, right? मिसाल के तौर पे अगर मेरा ये पॉइंट है तो इसकी u1 जो है वो होनी है, लेट्स से जिस तरह मैंने उस तरह फाई का लिखा था उस तरह होना है x1 प्लस 2x2 प्लस बस मे बी x3 शायद एक और आ गया, एंड सिमिलरली u2 की अपनी एक एक्सप्रेशन होगी, एंड सो ऑन. Just pointing out right here, okay, they will depend on each of them. Right? Hello, anyone there?
Yes, ma'am.
Okay, thank you. So Adan, is this clear to you? Okay, that's why I have these two separate indices. They do not represent free indices or dummy indices at all right now. All they're representing is that ui is a vector which depends on another vector xj. That's it. Because ये जो brackets हैं इनका मतलब है function of. Okay, so I hope that's clear. Now, so with this explanation, I hope it's clear when I write down the index notation of this equation. ये vector में लिखी हुई थी, और अब अगर मैं इसको indices में लिखूं, then this is what I'm gonna get. ui is a function of xj and time. Similarly, xi भी जो था, that's also a function of another vector, एक vector xj minus I have my xi. Now please notice here कि ये जो मैंने इधर मैंने small j use किया था just because we're more familiar with the small j's, and I've suddenly jumped to using a capital J एक वजह से, only because it has the same meaning as the small j right here. But all I want to do is I want to identify कि ये इस capital X का index है. ये reference position थी ना, capital X के index को मैं वही just थोड़ा और emphasize देने के लिए कि मैं reference configuration की बात कर रही हूँ, इसलिए उसके index को मैंने J से represent किया है, capital J से, sorry. ठीक है जी. So this will keep it will become more clear slowly. Please don't be too worried by this. Acha, now what time is it? Okay, 7:03. So Hassan, yes, we करने लगे. So we'll have it's 7:03. We'll restart at 7:13. Okay, smack 7:13. Or what I want to let you know is okay, I have a fun activity. So please be back at 7:13. 7:13. We need people for it. Okay, so 7:13. Be back. Okay, so 7:13. Let's start. So, okay, so I said that I've got a slightly interesting and I hope fun activity for you all planned. Can you please all raise your hand to tell me that you're here so that I can start? Otherwise, we're gonna have to wait a little because we need people for it. Excellent. Thank you very much. So that's perfect. Brilliant. We can start with that many people. क्या हुआ अमिताभ? कुल 7:13 ही है ना exact. Okay, so let's start. Basically, what I want you guys to do is take out your phones. Take out your phones and then open something called open a web browser. Yes, open a web browser and then go to this site, which is kahoot.it. Kahoot.it. So it stands for Kahootit. Now, it is very important that you do this on a mobile phone, not on your laptop, because the questions will appear on this Microsoft Teams share screen. And you have to answer on your app. Right? So if you go to kahoot.it, pop in your name. Please use your actual name so that we can, just your first name should be enough. And then put this game pin in so that we can play this game. So Saad's here. Excellent, Saad. Well done. Points for you for being the first one to make it here. All right. So hopefully more and more people are showing up. Excellent, excellent. Right. Now there's also if I let me know if you can hear this. So there's a little bit of a lobby music, but if I turn that on, then you guys can't hear me. So what I'll do is once the quiz, it's a quiz, ta-da! So once the quiz starts, then I'll pop up the volume of the Kahoot and stop speaking myself. Okay, now let me explain the rules of the game, basically. So as I said, the question will come up on our share screen in MS Teams. Okay, so you'll see the question there, but you have to answer it on your own device. Okay, so I know the first time it might take a little while to figure it out, but इंशाल्लाह इसके बाद से we'll get used to it. ठीक है, तो स्क्रीन हमारी MS Teams की मीटिंग की शेयर स्क्रीन के ऊपर क्वेश्चन नजर आएगा. आप लोगों ने अपनी डिवाइस के ऊपर आंसर करना है. और the way it's scored is basically whoever gets the right answer, but in addition to getting the right answer, whoever gets it the quickest. Okay, so you also have to try to be quick with your answers. Okay, so I think there are enough people here. So I am going to start now. 22 of us here, that's enough. And then I'm gonna adjust. So I'm gonna pump up the volume, and then I don't need to speak then. So please. Oh wow, some people thought it was ungraded. People, please, no, assignments are graded. Quizzes are going to be ungraded in this course, okay? All right. Asif, please try again. Okay, Amir, well done. You're right at the top position, but very closely trailed by Osman. Yikey doodles. Who are these 6 people who think that tensors depend on a coordinate system? Nope. That was the fundamental definition of a tensor, that they are independent of the coordinate system. Okay? So good on the vast majority. Well done. Amir is still at the top. Okay, so this question is a multi-select. There are more than one correct answer. Ooh, time is running out. Okay, all right, very good. So the people who answered got it correct, basically. So well done to you all. Only one person got a slight wrong answer. Well done, everyone. Okay, Amir has been dethroned. Usman is at the top. Again, another multi-select. This is related to the correct use of dummy and free indices. So which of these expressions are correct? Okay, no, vast sort of very large variety of answers. So basically, it was just this one was correct, which says that Aij is equals to Bji. There's nothing wrong with that. There are 2 free indices in each of the left and right hand sides, and the indices match up. So this is correct. And then in the green one, we have AIBI. So I is clearly a dummy index. And then K also being repeated. So that's also a dummy index. So these two are correct. Whereas what's happening with the red one? So in the red one, we have Aij is equals to BKL. Now, the issue with this one is that the free indices are not matching up. So this does not make any sense, basically. So that's the issue with this one. And the one down here, we have, yes, so most of you got this, did not choose this answer. We have 3 repeated indices. Sorry, an index repeated 3 times. Now that's not correct. You can only have an index being repeated 2 times. Okay, so that's why it was this blue and green which were correct. Let's see who's very nice. Essen. Okay, well done. Let's see what happens next. Ooh. Okay, so Kronecker delta. It represents the components of the identity matrix. So if I'm finding delta II, I'm finding its trace, aren't I? So I just have to add delta 1, 1 plus delta 2, 2 plus delta 3, 3, which is going to be 1 plus 1 plus 1. So it's actually 3. So the majority of you got it incorrect. So be careful, please. Delta II, this is II, it's the summation convention being applied. okay, on the Kronecker delta symbol, right? So I think this must have changed. Oh, Essen still got it right. So it's changed up the following positions, but Essen still on a answer streak. Well done, Essen. Second last question. What is AI, J? Excellent. Majority got it right, but a few people made a mistake. So please notice the red and the blue options were basically the same because they had a dummy index. It was a repeat index J delta del AJ divided by del XJ. So it was actually the green one. So del AI with respect to del XJ. That's what the comma represents, right? So, okay, so vast majority got it right. Last question, and then we'll see what happens to the podium. Excellent. So most people were listening in the past hour. So very good. Yes, it is indeed the Lagrangian description is the reference material description. So it's in terms of the capital X, not in terms of any of the other properties. Small x represents the spatial description. U is just the displacement, as we've just discussed, and phi was the mapping. So that was a function. It wasn't a variable. Excellent. So let's see. This was the end of the game. So let's look at the podium positions. Maurice. And then Amir got 5 out of the 7. I'm guessing this is going to be Essen. Very good, Essen. You got all of them correct. Excellent, excellent. And then just a few runners up as well, Usman and Noman. So everybody else, I think, was close by. So Amir and Maurice were close by, 4,700 points. Whereas Essen was in a league of his own. Excellent. All right. Thank you very much, all of you, for participating. I hope you enjoyed it. Just at least some way to make it a little bit more interesting to have a quiz. Now, please notice that, as I said, this is the way the quizzes are going to be in this course. So it's for your own assessment. I will start to have slightly more difficult questions in there. The purpose is for you to check your own concepts. So if you're going wrong somewhere, you know when you've got an answer which is incorrect, right? So well done to Essen, and then let's see if next time you can continue on your winning streak. Right. Okay. So with that, let's move back to where we'd left off in our kinematic description. So we were trying to describe the motion of a body, basically, right? So that's what we were doing, study of kinematics. And we'd gotten this far where we just started to describe what the displacement was. And now I want to move on to the next topic. Right, okay, let me just have a little sip of water. Okay, right. So what I want to do now is to emphasize that we've considered basically that when we have a reference configuration and a current configuration, then we can sort of see how a particle has moved from a reference position to a current configuration, either by looking at the mapping phi, or even by looking at the displacement that it has had, right? So even by looking at the displacement that it has had. So these two properties, so these two sort of functions, either the mapping or the displacement, will tell us where a particle which was initially at x has gone at some other time. But the issue right now is that sure, sometimes we're just interested in the motion of the particle, but more often, we're actually interested in the deformations that are happening in the vicinity of the particle. That is, we're interested in how the strains are developing around that particle in the body, let's say. Now, when we're considering strains, then basically what we're doing is we're looking at how there are changes in the sort of shape of the reference configuration in that close vicinity of the particle. So in order to do that, then we actually need to look at small positions away from our reference position and see that how is that small region around the particle distorting as we move to our new position, so to speak. Okay, so what I'm doing right now in this figure right here is I'm actually looking at a small position away from the capital X particle. Okay, even though I know I want to point out here, I know that I've drawn it out in a way that this is actually pretty big. So this arrow dx is pretty big, but I am that's only so that I can visualize it more clearly. Please note here that I am just looking at the close vicinity of a particle P. Okay, so close vicinity I'm representing by the D being there. So it's like a small change in the position X. So small change in capital X. Okay, so this new particle, which is just a small vector, small position vector away from the particle P, I'm going to call capital Q, which is at a time t0 in the reference configuration lying right here. So if I look at how this particle is deforming, then what I've got is that I've gone from Q being right here to Q being somewhere right here. And in my current configuration, then my particle is going to be just as it was a D capital X away from particle P. Now in my current configuration, it's going to be D small x away from the particle P. Okay. Why? Because this is my reference configuration, and hence why it has a position of capital X plus D capital X, whereas in the current or the deformed configuration, Q has a position small x plus D small x. Okay. Great. So I've got these. Now I can start to take a look at how I can write down this xi plus dxi, that is the final position of the particle in terms of its reference position. So for that, I'm going to use the mapping that I had previously, right? So my small xi plus dxi, that is the current position of particle Q, can be represented using the mapping, right? So this phi was my mapping that was taking me, which is giving me a function. Please notice again that this is a function. This is the mapping function such that if I substitute into whatever expression it may have, I don't know what the exact expression is because I want to keep it general. So if I substitute into my mapping function whatever my initial position of the particle was, then I'd get its final position. That's why I've popped in capital X plus D capital X. Okay, this will lead me to the new position of the particle Q. Now what I'm going to do now is that I'm going to use some sort of approximations in calculus where I can expand a function out using its derivative, right? So I hope you all are vaguely familiar with small changes and how we can use them in calculus. So if I expand this function out till first order, then I get that this same old expression, this one, is approximately equal to, it's approximately, I know, but it'll make do because I'm in a small sort of, my dx's are small. Then this is approximately equal to the function evaluated at x plus the derivative of the function multiplied by the small change that's occurring in its argument. Okay, what this means, I may have to explain this a little bit more. Okay, what this means is, imagine imagine I have a function. I'm just going back to normal geometric representation. So I have a function y as a function of x, let's say. Okay, something like this. So if I want to find, I already have this position x. And let's imagine that I want to find my y at a small displaced position from x. So I want to find it at, this is going to be my dx. So I want to find, this was yx. What I want to do is I want to find y at x plus dx. Then what I can do is consider that my dx is small. So using that approximation, I can consider कि okay, ये y x plus dx तो actually ये हो गया कि मैं इस वैल्यू के अंदर जो मैंने y of x पे निकाली थी उसके अंदर एक स्मॉल dy ऐड कर दूं. ठीक, राइट? क्योंकि अगर मैं इधर जूम कर सकती होती, आई हैव ड्रॉन इट आउट सो स्मॉल, बट कंसिडर कि ये y of x था इधर, और पर हल्का से ऊपर जो आया था ना उसके अंदर स्मॉल चेंज हो गया था जो dy था, लेट्स से. ऐसा ही है. So that's why I would have got y evaluated at x plus that small change in dy. Now this small change in dy is actually, अगर मैं उस ट्रायंगल को थोड़ा सा ट्रायंगल ही बन गया ना, अगर वो कर्व था तो उसका टेंजेंट से करके, what that becomes is actually, if I have the gradient or the slope of this curve, then this yx plus dy by dx multiplied by dx. Why? ये इधर dy by dx को मैं specially represent कर रही हूँ. This is the gradient of this thing. So it's dy by dx because it's this sort of tangent theta. Now you could look at it two ways. Either you can consider that because वो dx's cancel हो जाते हैं, that's why you get the small change in y using the gradient. या फिर what I was trying to do by drawing the triangle was to notice कि I know कि ये tangent theta जो है ना, that's equal to dy by dx. तो अगर मेरा कोई स्मॉल चेंज हो रहा हो उसके अंदर x के अंदर, डेल्टा x हो रहा हो, फिर उसी का कॉरेस्पॉन्डिंग हाइट का चेंज वुड बी आल्सो बी इक्वल टू tangent theta, such that I get dy by dx is also equal to delta y by delta x, so that I get my delta y, small change in y, is actually equal to the gradient multiplied by delta x. ठीक है, तो सॉरी मुझे इसको ना, I should have started by representing this as a delta x ताकि gradient का dy से ज़्यादा clear हो जाता. Right? So यही principle जो हम लोग, we are so familiar with using in standard sort of geometric calculus जब हम कोई graphs और plotting functions को consider कर रहे होते हैं, that also holds true for field variables being defined in space. Yeah, for other sort of physical properties, such as the mapping that I have right here. So that's why when I expand this one out, that is that I'm finding this function. ये बिल्कुल y की तरह ही है, एक function है. When I'm evaluating this function at x plus a small change in x, then I can actually write it down as that function evaluated at x plus the derivative of that function with respect to x multiplied by the small change in x. right? Now this is, I've only expanded it up till first order. This actually sort of an approximation goes onwards. वो क्या था? Taylor theorem, yeah. I think that's what it was. Yeah, Taylor theorem key expansion. You can carry on with the double derivative or triple derivative and so on. It carries on to get the equal sign. It's an infinite series. But please notice that I'm just operating within the small region of space around that particle. So my dx's are actually pretty small. So as I go up to the higher order terms, I'm just going to keep adding into it dx squared per dx cube ka term and so on, which I don't really need to include. That's why I've just included it up till first order. Okay. Is this clear to everyone? Please, someone acknowledge.
Yes, ma'am, it's clear.
Thank you, SN. SN, आपको तो मुझे लग रहा है I need a few more people to acknowledge because I am wondering if anybody is actually listening. Thank you, SN.
मैम एक क्वेश्चन था।
हाँ जी, प्लीज।
मैम ये जो डेरिवेटिव टर्म है ये कोई फील्ड रिप्रेजेंट कर रही है, लाइक वेक्टर फील्ड आई थिंक।
जो डेरिवेटिव टर्म है इधर डेल फाई बाय डेल एक्स।
यस मैम।
ये वाली।
यस।
एक्चुअली अभी हम देखते हैं कि ये वेक्टर फील्ड है या ये टेंसर फील्ड है या ये क्या है। जस्ट गिव मी 2 seconds and we'll get to what this thing is. ठीक है जी।
ओके मैम। ओके
राइट। बट यहाँ तक ये एक्सपेंशन तो सबको आई होप कि क्लियर है ना। अब आते हैं हम जरा सा थोड़ा और आगे मूव करना, which is to notice कि if I just have the mapping at x, मतलब ये if I'm just going from this and then applying the mapping to it, then I just end up at xi, right? So the mapping applied at this reference position just gives me pt, x पे आ जाती हूँ मैं, right? So using this substitution, I can substitute this back in here to notice कि ये phi I x तो actually सिर्फ xi ही है, which is why it cancels out from the left and the right hand side. And I just end up getting that dxi is just equal to the del phi I with respect to del xj dxj. या फिर rearranging it even more such that मैं इस चीज को represent करने के लिए एक नई expression ले आती हूँ और उसको मैं सिर्फ एक f, capital F से represent कर लेती हूँ. Then my fij, this thing is actually ये वाला differential. It's del phi I with respect to del xj. Where again I'm gonna be a little sneaky and substitute in कि phi I evaluated at x, ये जो चीज थी phi I evaluated at x, वो तो था ही small x, so that this expression can actually be written as phi I evaluated at capital X is actually just del of xi with respect to del of xj. And this thing I'm going to represent as this new, I'll discuss कि क्या है ये fij is equals to this thing. Okay, so I will carry on, but just again, is this small tricky thing a little clear? So I'm saying that if I have a point capital X, you see capital X है, और इसके ऊपर मैं अपनी मैपिंग अप्लाई करूं, then you all recall कि उसी मैपिंग के जरिए से तो हम इस पे पहुंच रहे थे, इस पॉइंट पे, जब हम इसके ऊपर phi लगा रहे थे on capital X. So that's why this mapping applied at capital X basically leads us to the small x, and hence why I've got small xi. ठीक है जी. So I hope I'm not pulling too many things out of thin air. Just a few things here and there. Right. Okay. Now this is quite quite important now. So we're coming to, we've seen कि हमारे पास एक ये derivative आ गया है, del xi by del xj, जो कि we can use to represent my dxi. मतलब ये कि जो मेरा small change था in the spatial coordinates from my initial position, I can represent this in terms of my small change in the reference configuration by using this f tensor. And notice why I can, मैंने ये expression कहाँ से लिखी है? Because I know, ये देखें ना, अगर मैं dxi मैंने लिखना हो, then I can write it as del xi del xj into dxj. ये dxj और del xj cancel हो जाते हैं, and hence why dxi will give me del xi, right? Derivative और उसी की definition से I'm coming to it. So if I represent this derivative with this symbol Fij, then I can describe this a little bit more compactly. Now notice this dxi is a vector. This d capital Xj is also a vector. And then this Fij right here, which is relating the two, that is, we can see has two subscripts, two indices. This is a second order tensor. और also index notation की rules भी ये follow कर रहा है सब कुछ या नहीं उसको notice कर लें. On the right hand side, my capital J's are my repeated indices. So that's why वो dummy index है. ठीक? तो इसकी वजह से they will disappear and I will only get my free index left. And hence why वो free index match कर रहे हैं. Now also please notice इसी expression को अगर मैं चाहती ना, so I could have easily, there's nothing different in writing this as dxi capital F I j small j dxj, या फिर जो मैंने ये लिखी हुई है, मैं सिर्फ और सिर्फ ये स्मॉल j के बजाय कैपिटल J से लिख रही हूँ ताकि हम सबको ये बात याद रहे कि ये जो dx के साथ है ना, जो भी डिफरेंशिएशन हो रही है एंड सो ऑन, that is with reference to the that is with respect to the reference configuration. That's the only reason. ताकि जब मैं Fij को लिखूं, then I know कि वो del xi with respect to del capital Xj है, so that I know कि मैं इसको इस तरीके से भी लिख सकती हूँ, x वही comma notation use करके for differentiation. That's the only purpose. Okay, so it's just to emphasize the fact that it is in the, it's derivative, it's the differentiation with respect to the reference description of position. और derivative है किसका? इस spatial in the next position जो उसका vicinity है उस particle की. Okay. This now this अभी मुझे I forgot your name, sorry. You'd asked के what is this derivative? Is this going to be a vector or a tensor? And as we've seen that this is actually a second order tensor, and this thing is known as the deformation gradient. This Fij is known as the deformation gradient, and this is actually, it's del x with respect to del capital X. Now remember that we did have a something called the del operator. सबको याद है, अब वो हमने अभी थोड़ी आज ही के उसमें किया था. del operator एक वेक्टर था जिसके अंदर del by del x, del by del y और del by del z था, right? तो इसी डिस्क्रिप्शन को लेके ना हम एक और ऑपरेटर को डिफाइन कर देते हैं which is del not. And the purpose of the not is to represent कि वो जो differentiation हो रही है, that's with respect to the reference configuration. मतलब ये कि del not is equals to del by del x1. del by del x2 and del by del x3. This is what del naught represents. Okay. Okay, right. Yay, this is just इस text के अंदर वही चीज है which I've already discussed कि capital J और del naught बार बार इसलिए यूज हो रहे हैं because it's important to emphasize कि वो differentiation is in the reference coordinates. Okay. And that's why this deformation gradient, आमतौर पे जब बंदा कोई deformation gradient कहता है ना तो उसका मतलब ही यही material या Lagrangian description वाला deformation gradient होता है. कभी कभी एक्चुअली लोग स्पेशल डिस्क्रिप्शन वाला या फिर डेल बाय डेल स्मॉल x1 डेल बाय डेल स्मॉल x2 एक्सेट्रा वो इतना यूजफुल इसलिए नहीं है क्योंकि आमतौर पे एज यू ऑलरेडी डिस्कस स्पेशल डिस्क्रिप्शन यूज हो रही होती है फॉर फ्लूइड्स और फ्लूइड्स आमतौर पे आर most of them tend to be incompressible या फिर even if they are compressible उसके अंदर we're not really interested in these deformations. What we are interested in is the rates of their deformation for fluids, whereas for solids we are actually interested in the deformations themselves. Okay, we'll slowly start to emphasize these aspects even more. Just give me a few more minutes and then I will wrap up for today. Okay, so just want to emphasize that if I expand out this expression del xi with respect to del capital Xj, then what will I get? I will get a second order tensor. Second order का मतलब ये it's a 3x3 matrix के तौर पे वो represent किया जा सकता है, and that's what the terms would be, right? Del x1 मतलब जब I1 है इस केस में और इधर जो columns है that represents when j is equals to 1. Either I is equals to 2 and so on, right? So del x1 with respect to capital del x1, del x1 with respect to capital del x2 and so on. I hope this is clear to you all. So this deformation gradient contains the derivative of each of the components of small changes in x, small x, with respect to each of the components of capital X. Right. Oh, yes. So a small side note to consider, which is कि हमने एक और vector को भी देखा था, which was the displacement. I think you all recall, right? So displacement was also giving us how we could go from small x to capital X, right? So is vector notation say I can write down that my u is actually equal to small x minus capital X, जो मैंने पहले ही लिखा था for my displacement vector. So rearranging this I can get my expression for small x, and if I substitute this in here, let me substitute this. क्या हो गया मेरे पेन को? Substitute this in here, then I get x is capital X plus u, which means I can the derivative operator, the del operator is distributive, so I can expand this to be del x with respect to del x, which gives me an I derivative with respect to the same thing, that's just an identity matrix, plus del u by del x. ऐसा ही है ना? So I can write this out. ये अब displacement की terms में हो गया my deformation gradient. I will discuss this thing later on as well. अभी फिर मुझे I think I have a feeling कि अदनान कहेंगे ये सब क्या description पर description आई जा रही है, सब कुछ का physical मतलब क्या है, physical मतलब. So what I'm going to do is, since I'm running out of time, yes, in case मेरी tone से आपको पता नहीं चल रहा था, this deformation gradient is a pretty important thing. It pops up all over the place in solid mechanics and maybe even sometimes in fluids, but it pops up all over the place in solid mechanics. Or I will, as I said, I will assign assignment 1 this time around, But by the time we're in the middle of kinematics, I'll be assigning you an assignment too, जिससे आपको इन सारी जो all these properties that we're describing right now, उनकी research use भी नजर आनी शुरू हो जाएगी, I hope. Okay, so my point is I am going to end here at the deformation gradient. And next time, inshallah, I will pick up with some examples of the deformation gradient. Okay, when we have some particular types of motion, what does the deformation gradient look like? Okay, ji. So we'll pick up there. As I said, there is going to be an assignment. और assignment जो है वो आप MS Teams के ऊपर ही submit करेंगे. So you just need to, once you solve the assignment, you just need to take a picture. It should be legible. I should be able to see and read it, and then upload it as your submission on Teams. Right. So that's it for today. Anybody with anything unclear and some remaining questions? Hassan, आपका वो question clear हुआ या नहीं हुआ था वो कि वो ऊपर ही हो अगर तो फिर क्या होगा?
मैम वो क्लियर हो गया था फिर.
Thank you so much. Thank you, Hassan.
वो
Okay जी,
मेरे
sorry.
concept में थोड़ी weak थी. मेरा concept थोड़ा weak था.
नहीं, no problem. जी, somebody else was asking a question and I interrupted. Apologies, please. Go ahead.
No problem, ma'am. Not a question, just a request. जहाँ से आपने deformation gradient में expand किया था first order, वो जो series expand किया था, next lecture में वहाँ से please start कीजिएगा.
ओह, क्यों? उसमें तो मुझे आधा घंटा इसी चीज में नहीं लगा था वो सीरीज एक्सपेंशन के अंदर.
मैम आप 6:30 पे नहीं 4:30 पे स्टार्ट कर लीजिएगा.
ये कौन बोल रहा है? आप ऐसा नहीं करते कि आप रिकॉर्डिंग देख के आ जाइएगा.
श्योर, नो प्रॉब्लम.
ये भी तो हो सकता है ना. आप ये वाला पार्ट देख लीजिएगा प्लीज. सामा
अगर
प्लीज.
कोई मसला हुआ देन.
हाँ, फिर तो you ask me right then and there and we'll deal with it. No problem.
Okay, sure ma'am. Thank you.
Thank you, Sama. Okay, deadline for the assignment. I haven't decided yet. It'll probably be about a week or 10 days, roughly. Today is Tuesday. It will quite possibly be sometime next week. Okay. All right, Ji. Thank you so much to all of you. Inshallah, see you all next week. If not in person, then definitely online. Take care of yourselves. Okay. Allah Hafiz.